good exercise for you. So I did it. So I claimed territory. That's what I did. It's very good. I did it by induction, actually. So we have this. So we know that our sequences satisfy this recurrence. And now if we have this, then we can do a lot of stuff, like we can find generating functions and so on. Basically, by the previous theorem, we know that the sequence AN satisfies this. Now, the exponential sum was actually equal to this. You remember, right? That's basically what we did. Now, the characteristic polynomial associated to this recurrence, 2 is actually a root of it. So this thing satisfies the recurrence, and so is this. So the linear combination satisfies the recurrence. It might not be minimal, right? I know that the exponential sum now satisfies this recurrence. Maybe another one that is minimal, but that's okay. That's what we have now, and because of that, then it's now not hard to calculate the generating function. It's actually it's not a big deal. So the previous theorem, for example, we know the first one is this. For 4, we have this. This one collapsed, right? So it's simplified to this. So that's probably because there's a smaller recurrence here. The big one's that, and so on. Next, I move to calculate the exact values of the exponential sum. Now, I know that there are actually formulas for it, but I just want to do it with the computer, right? That's basically the goal here. So, in this case, we will apply the standard technique, right, of finding a solution of a recurrence. In this case, this is our characteristic polynomial. And the trick happens once you realize that P is actually this Q here, but shifted a little bit. Okay? So if you let Q equal to that, then you have this. So we know the roots are all different. And more than that, have this form 1 plus theta, where theta is a 2 root of unit. So now we know this. So we know that our exponential sum actually satisfies this formula, so it's invariant. Basically depend on k but not on n, right? You want to find something in n, just plug the n there. So
was this the formula that Mathematica gave you originally?
No, Mathematica, when I plugged the exponential sum as it was, it gives me something in terms of sine and cosine. But this one you can manipulate and get that.
So it's equivalent.
It's equivalent, yes. I just wanted to see where this thing was coming from. But the very first time that I did it with Mathematica was actually a guessing thing, because I just could find sequence functions, so I give a certain amount of values and then Mathematica guess it. But if you put the this sum there, Mathematica actually calculates in terms of sine and cosine. For example, for the k equal to 3, we just use our computer, right? So in this case, we know this. We put the first 3 values, of course, not of this, but of this. These are the values. So you use your computer, you get that. So our exponential sum is given by this, and that simplifies to this. And that's the answer that Mathematica gives. Of course, it gives you something more ugly, but then you could simplify and just start tweaking it, and you can get there. Sorry? Yeah. And other examples include this one. This is the 4th one, or the 7th one, which is that. But then you get tired after doing this. You want the computer to actually do it, right? Another thing that, okay, but this is just for the simple symmetric polynomial. What happens if you have more than one, right? And this is part of the work in progress. In this case, yes, we have recurrences. I still don't know them, so it's time for the computer to actually do the work for me, because my brain is getting tired watching that. So, but it seems that the recurrence is actually dictated by the maximum of the degrees that we have. And in this case, for example, if the maximum degree is a power of 2 or minus 1, then the recurrent seems to be this ugly thing. Enough with that. Now it's time for the computer to do the job for me. This is it. Happy birthday, Dawn.
Any questions?
Yes.
It may be that writing exponential sums in terms of counting points over varieties over finite fields, plus the wide conjectures proved by Boolean, imply that for any polynomial, this sum satisfies a constant coefficient linear recurrence,
Yeah, that's
where
what
the
I was thinking.
exponents, which are the roots of the characteristic polynomial, are explicit algebraic numbers that satisfy also the wide conjecture bounds.
Yeah.
You may get an existence theorem like that, I'm not sure.
Or if you don't know if it's constructed. But I mean, I'm expecting that many of these things are known. What I want to do now is actually to go, as you said, to go to extension of the ground field and then move to the side and see if we have a recurrence here, what is the relation between that recurrence and the one that we just found there. So that's what I'm planning to do. But I expect that what I did here is no. That's what I think. I mean, Mathematica knows how to do it, so probably it's not. Yeah, but we should.
But the wide conjectures are not constructed.
Okay, I see.
That existence theorem is not
Okay, I
achieved.
see. I see. So we know that satisfy the linear recurrence,
That's
but we don't know.
another
We don't know.
story. Yeah.
Okay. Okay.
Let's thank the speaker again.